In this video, you will learn how to evaluate the performance of a regression model using the Numeric Scorer node. Ready? Let's get started. Regression models predict a continuous output such as the amount of a credit, weekly working hours, or person's income. Numeric Scorer node outputs a table including different evaluation metrics to assess the model's prediction power. For example, in our model, the average absolute error in predicting the amount of a credit is 45 euro. We can also assess the share of the variance of the target column explained by the independent columns. For instance, demographic data like age, gender, and education might explain 75% of the amount of a credit in our model. Some evaluation metrics allow for comparing models with different target columns, while others allow only for models with the same target column. Suppose you have a model that predicts a credit amount with an average error of 45 euro and another model that predicts weekly working hours with an average error of 2 hours. You cannot say which model performs better based on these metrics alone. However, if the first model explains 60% of the variance of the credit amount and the second model explains 80% of the variance of the working hours, and the number of independent columns is not very different, you can say the second model performs better. Let's take a look at the workflow that trains and evaluates a regression model. Here you read and pre-process data to train a linear regression model and apply it to the test set. The problem at hand is to predict the amount of a credit. The data include information on credit customers such as their credit history, credit purpose, property, and credit amount. The input data of the Numeric Scorer node must include at least 2 columns, one for the actual data and one for the predicted data. Therefore, you can connect it to the regression predictor node or any other node providing these 2 required columns. Next, you open the configuration dialog of the Numeric Scorer node. Here you define the reference column, which includes the actual values. In the second menu, select the column including the predicted values, the prediction credit amount column. In the output column section, you can change the name of the column that includes the evaluation metrics in the output table. If you enable the option at the bottom, the evaluation metrics will be provided as flow variables in the output of the node. You can also add a prefix to the flow variables' names. Click OK and execute the node. The evaluation metrics are shown in the output table, and the same metrics are available as flow variables in the Flow Variables tab. The first metric is R-squared, which is about 0.6 in this case, indicating that other credit data explain about 60% of the variation in the credit amount in the linear regression model. Other metrics in this table tell us about the size and the direction of the error. Mean absolute error. The average absolute error between the actual value and the predicted value is 1256. Mean squared error. This metric is commonly used in optimization processes but does not have an easy interpretation. Root mean squared error. The square root of the mean squared error. It has the same unit as the target column. Here the error is 1794 euro, which is bigger than the mean absolute error because this metric weights the big differences more. Mean signed difference indicates that on average, the model tends to predict 32 euro too high credit. This metric informs about the direction of the error, not the size. Mean absolute percentage error. The average size of the error relative to the actual value. The model predicts credit value within the range of the actual values plus or minus 57%. In this video, you learned how to evaluate a regression model with a Numeric Scorer node and how to interpret the results. You have also learned the different purposes of a model evaluation and the limitation of the metrics. Remember, while the evaluation metrics quantify model performance, they do not tell if the model assumptions such as no multicollinearity, homoscedasticity, and normality of the error terms are violated.